last and final topic that we're going to talk about is the idea of using rational expressions, rational equations to actually address real-world scenarios. Oftentimes, some of the problems we're about to run into are ones that people joke about, ones that show up on ACTs or SATs or show up in movies when they sound almost so ridiculous that you're like, how do I even begin to approach this? And the truth is, oftentimes, ones where train A leaves this station and train B leaves this station, when will they collide? The idea behind that actually goes along with the idea of a rate. If you think about the idea of a rate is expressed as a fraction in comparison of two ideas. And that second you hear that word fraction, ideally you can think, okay, a rational expression is a fraction in comparison of a polynomial over a polynomial. So we're going to start by looking at this problem, which actually has real-life implications. You've got one person who can do a new coat of paint on a gym floor in 24 hours, and a second person who can do it in 28 hours. It makes sense that you need to know how long will it take if they both work together. Now, oftentimes, the quick answer is that people want to either average or subtract or do some sort of combination, but in reality, we're going to use old-school ways of solving word problems, taking that last sentence and saying, okay, how long would the job take? We're going to say, you know what, I don't know exactly how to approach this, but I do know that my unknown is the hours it takes for both to complete the job. I'm going to refer to these often, especially when I get back, as job problems. And the idea behind job problems is typically we want to complete one job. So if we're talking about Mrs. Heiner's rate, we could say for one job, it takes her 24 hours. And for Mr. Hunt, it takes him 28 hours. The idea of one job per 24 hours. It really is a rate. Well, if you have Mrs. Heiner's rate and you combine it with Mr. Hunt's rate, the combination would be their together rate. Their together rate. One job in X hours. Now, what you then need to be thinking about is just old school with the most basic, really, of rational equations, where I can say, all right, how do I solve this? Well, I find a common denominator really quickly just for ease. 24 times 28 is 672. So I could say my common denominator is 672x. This would be 28x plus 24x equals 672. 24 plus 28 is 52x equals 672. And 672 divided by 52 is 12.92. 12.92 what? It's going to become really important that we clarify our what in this case. And in this case, hours, what we've solved for is the number of hours to complete the job together. Now notice that is neither an average or a subtraction. It's none of those options. It should make sense that, yeah, together they can do, even this part hopefully makes a little bit of sense, a little bit more than 12 hours. If Mr. Hunt had worked at the exact same rate, they could have done it in half the time, but he could not, so it's a little bit more than half of Mrs. Heiner's rate. So that part of just a numerical sense hopefully makes sense. But what I want you to do now is hit pause and just take a minute, if you would, please, and just read through this idea of setting up a complicated word problem. And then if you would, go ahead and read this to yourself. This is going to sound quite similar. It's purposely set up that way. And then what I want you to do is hit pause, read it, name your variable, and then think through, okay, this is a job problem. What is a job? And what are the ideas that are working together in this scenario? So in that last question, how many days? That is the number of days they will work together. in this job. And we know that Joe can do one job in 6 days. Courtney's crew can do one job in 8 days. And their combined work can do the job in X days. Ideally, you can crank through this. If you want to, go ahead and hit pause to solve. I often think it's easiest to just take 6 times 8. You obviously could use 24 as well. 48x, this is going to give me 8x plus 6x equals 48, because I use 48x as my common denominator. This is 14x equals 48. So x equals 3.4 days to complete the job together. Now, this is style 1. We're going to now move into a second style. I refer to this often as a style on travel. So in this style, we're going to use rates, but it's going to sound a little different. Will you take a minute and hit pause and read it to yourself? So the first thing that I want you to get in the habit of is going to that question and naming my variable. I know that my unknown that I'm going to try to find is Jamie's bike speed. And I do know one more idea, and that is that if I take my bike speed and add 43 miles per hour, I actually have Jamie's driving speed. And that's going to matter here in a minute. I'm going to also remind you of something else, and that is that oftentimes in word problems, we are looking for a total. In the previous problem, we were essentially saying our total was the completion of a job together. In this case, we've got a total that has an entire trip of 1 hour and 40 minutes. Now, just quickly notice we're in miles per hour here, miles per hour here, and so we have to think about this in terms of hours, because my speed is given in miles per hour. The sheer fact that I am given a total, I identify it as a total time, and in identifying it in a total time, I'm clarifying that what's happening over here is about time. That is the same idea as this. I had a together rate. That together rate comes from Mrs. Heiner's rate plus Mr. Hunt's rate. The sum of these rates gives me a together rate. Similarly, Joe's crew is a rate. Joe's rate plus Courtney's rate is their together rate. Well, I'm going to have a time from UA to Sunbury and a time from Sunbury to Mansfield. It will give me a total time. That total time is 1 hour and 40 minutes out of 60. If you reduce that, that is 5/3 total time. That's 1 2/3 hour. Now, I got to think what time is. This is why these travel problems can be a little tricky, because I need to go back to old school in terms of mathematical ratios and connect the fact that the very first time I ever talk about rate and time connects distance with rate and time. So if I need to talk about just time, that is actually talking about my distance over my rate. So I know my total time. What I need to know is what's being added together. Well, there are two parts to what's being added together. A trip from UA to Sunbury and a trip from Sunbury to Mansfield. This first trip is going to have its own distance and its own rate. This second trip has its own distance and its own rate. Do me a favor, hit pause for a quick minute. If you need to, rewind and listen to that conversation, but before you do, I want to say this summary. This has similarities to the last type of problem in that it still has a total. The previous problems had a total togetherness rate. This has a total time. What's happening on the left has to be the same concept as on the right. So what is being added together on the left is total time. It equals total time of the entire trip. So hit pause, rewind, and listen if you need to again, but then we're going to talk about what goes in here as distance over rate and distance over rates. my UA distance from UA to Sunbury is 17 miles. My rate, we already clarified, was what it was the bike speed. She was taking the trip from UA to Sunbury by bike. Her 53-mile trip from Sunbury to Mansfield was by car. Distance over rate plus distance over rate, time plus time equals time. So now we're going to take this and we're going to solve it. So just so we can see that a little more clearly, go ahead and hit pause. This has a little bit more sophistication in terms of solving a rational equation. Hit pause if you would and solve. Go. Okay, so if you notice, my common denominator is 3x and x plus 43. When I multiply through, I'm going to have 17 times x plus 43 times 3 plus 53 times x times 3 equals 5. My 3's cancel, times x plus 43. Now, this is going to turn into a quadratic. So if you would, for me, please, go ahead and hit pause and work your way through until you get to the quadratic. This gives me 5x squared plus 5x minus 2193. Now, I would not expect or want you to actually solve that. I would want you to throw that in your calculator using the quadratic formula and come up with an answer. When you get your answer, you're going to have your bike speed. When you take that value and add 43 to it, you're going to have your driving speed. And then what you have here is your first answer to a travel problem. So go ahead and hit pause and make sure that you can use the quadratic formula properly. Compare your answers with one another. Double check that your bike and driving speed makes sense. But then in this case, what I want you to do instead of me giving you the answer, I want you to get in the habit of naturally plugging it in to check. When you get an answer for x, you should be able to plug it in here and in here. And in your calculator, plug it in and make sure it equals 5/3. You will have a calculator for this portion of your test next week. I want you to get in the habit of checking your answers. So get an answer for x, using the quadratic formula on that quadratic, plug it in, and make sure that you get 5/3. All right, that is the gist. Your homework is to do worksheet number 1 as referenced. And tomorrow is a work day, so you can catch up on all the details that are also referenced on the sheet itself, the actual schedule sheet that I gave you on Tuesday. All right, this is the last video for the week. I hope you have a great rest of your week.